Hi, everyone. I hope you're doing well. We've been talking about the multipole expansion of the potential, and today we're going to continue developing this idea. Just to introduce the idea again, the multipole multipole expansion of the potential allows us to find approximations for the potential due to an object. And it works like this. Imagine I have an object, maybe a charged object that has some complicated shape or some complicated charge distribution. Maybe it's this eraser here. Suppose this were charged. Well, since it has an unusual shape, the potential close to this would probably be very complicated. Hard to describe. But if we were very far away from it, over here, then the potential due to the eraser might look approximately like the potential due to a point charge that carries the same amount of charge as the eraser. As we get closer to it, we'd start to see a more complicated picture. We'd have to correct our potential with additional terms. The closer we get, the more complicated things look. Now, what the multipole expansion is useful for is when we're in this intermediate to far away situation, when we don't need to know all the details of the exact potential around this complicated object, but where we can make an expansion and just keep the first few terms in our expansion to describe approximately what the potential looks like. Okay, well, that's kind of the motivation behind what we're doing. Now I want to turn to an outline and talk about what we'll do today. Okay, so we're going to keep talking about the multipole expansion of the potential, which, as I said, lets us to get an approximate form for the potential when we're generally far away from some object. Maybe we want to find the electric field a few nanometers away from a molecule or something like that. In any event, last time we were able to write down the multipole expansion for a point charge, and for multiple point charges. And look at an example. I think that we covered extended charge, but I'm not quite sure if we got all the way through that. So in a moment, we're going to do an example of calculating the multipole expansion of the field around an extended charged object. And well, if you've already seen this, you can just skip that. Okay. Today, we'll show that we'll see that we can describe the different terms in the multipole expansion in terms of properties of our source, properties of our object. Okay. So we can say that the object carries a net charge, for example. That would be its so-called monopole moment. And in addition to the monopole moment, the total charge, the object might have a dipole moment and even quadrupole or higher order moments. So we'll introduce that idea, and then we'll talk mainly about the monopole moment, which is very simple, and about the dipole moment, which is more interesting. Then we'll use what we've learned to find the electric field due to a dipole moment. Okay. Finally, I'd like to talk briefly about forces on a dipole due to an electric field. a subject that'll make a little more sense once we've talked about, about what a dipole is. There we go. Okay. So let me quickly review the main ideas from last time. Last time we introduced the multipole expansion. Okay? And the multipole expansion basically let us find the potential around some object that maybe has a complicated shape or charge distribution when we're far away from the object. Suppose our object has size A. Well, then we want to describe the potential when we're a distance r from the object, where r over A is usually a large number. And what we do is we're going to expand the potential due to the object in a power series in A over R. So if we're far away from the object compared to its size, then A over R is a small number. And as we look at the terms in this power series that go like A over R squared, and so on, the terms will get smaller and smaller. And the idea is that we can get a reasonably accurate description of the potential with just the first few terms in the series. We found that since, rather miraculously, the distance between some point and the origin, script r, can be written as 1 over r times the sum n equals 0 to infinity of r prime over r times p sub n cosine theta. Okay, so yes, this is a expansion of 1 over script r, which is the distance from a charge at location r prime and our field point at location r. And you can see that we've been able to expand it here in, there we are, in powers of the source coordinate r prime and the field coordinate r. So since we can write 1 over script r in this way, we can write the potential, for example, due to a point charge as 1 over 4 pi epsilon naught times the sum over all of these terms. We had a term 1 over r that goes outside of the sum. And then we had all of this, r prime over r to the n, p sub n times cosine theta. Whereas where these terms, p sub n, represent the nth order Legendre polynomials. Looks awfully complicated, right? But it's not so bad. Finally, we said for an extended charged object, that v sub r could be written as 1 over 4 pi epsilon naught times the first part of this looks just like our sum from before. One over r to the n times the integral over the charge density of r prime to the power n times the nth Legendre polynomial. Excuse me there. And it looks like I need a little more room. Let me slide this over. Okay. And a prime there. Okay, so that's basically what we introduced last time. And now I'd like to stop this video. The next video we'll do an example, and then after that we'll get started on the new material.